In this video, I will show you how to reduce the dimensions of the given data set using PCA algorithm. So PCA means principal component analysis. So principal component analysis. So it's an algorithm that we commonly use to reduce the dimensions of the data. So especially if we have a very big data. So whenever I say dimensions of the data, it refers to rows multiplied by columns. So if we have, for example, x1, x2, x3, say xn, y1, y2, y3, say yn, z1, z2, z3 until zn. So if you count here, you have n rows and then you have 3 columns. So the dimensions of this type of data will be equal to n multiplied by 3. So something like row multiplied by column. So that's how you define the dimensions of the data set. So row comes first and then column after. So what do I mean by reducing the dimensions of the data means we try to reduce the number of the column. So if we have, for example, say like 11 rows multiplied by 10 columns, we can apply PCA algorithm and then you can reduce the dimensions to 11 multiplied by 1 or 11 multiplied by 2, so that the data in this part 11 multiplied by 1 or 11 multiplied by 2, which means 11 rows and 2 columns, is more than enough to represent approximately more than 95% of the data. So that's the idea behind PCA. Maybe I can upload a separate video on the PCA algorithm and how it works and so on. But for the moment, I'm going to assume you already know what's the PCA algorithm and the steps involved, and then we are going to use that algorithm to reduce the dimensions in the given data set. So what we have here, so I put a model example. So the goal is to obtain the principal components, which is here, just to follow the line, and we have to reduce the dimensions of the given data set. So what we have here is a crystal type. So you have in total 6 samples. I will just put sample number here, 1, 2, 3, 4, 5 and 6. So what this 6 sample means? So just imagine we performed some crystallization experiment and then we took 6 crystals, 1, 2, 3, 4, 5 and 6, and then we analyzed each of these crystals under microscope, and then somehow we managed to obtain length and the width of the crystals. And then under the microscope, what we observed is 3 of the crystals have needle shape, and then 3 of the crystals possess or looks like a spherical particle, something like this. So we have the length and then the width of these crystals, and you have the data here. So you have 287, 41, 294, 42, 273, 43. So this is obviously, it corresponds to needle. As you see, length is roughly 3 times or maybe even more larger than the width. So that represents typically a needle shaped crystal. And then here you see length and width, they're almost similar. So this is something that you can expect for a spherical particle. So length and width will be almost same. If you plot this given data in a small graph, just say like you put length on the x-axis, you put width on the y-axis, just say 200, this is 400. Let's assume length or width are expressed in microns, and then let's say width you have 100 here, you have 0, 0 on the axis. If you plot them, you will see something like this. Yeah? So this is something that corresponds to needles. So if you see here approximately 80, So length and width are same for spheroids, so spherical particles. So you have your spherical particles here. So why do we draw this graph? If you look at the graph, one thing is clear. You have length on the x-axis, width on the y-axis. So that's already 2 dimensions. So you need 2 dimensions to represent or to show that there are 2 types of crystals or 2 categories in the given data set. So when you apply PCA, what you're going to do is you're going to reduce this dimension, 2 dimension, into maybe 1 dimension, and still you can show that there exist 2 categories in the given data set. So that's the main idea behind PCA. So you reduce the dimension of the given data set. So this is just an example to understand PCA, but obviously in real world we use PCA when we are going to deal with a very big data set, something like say 1000 rows, maybe 100 columns, or maybe even 200 columns. 200 columns, we can reduce everything into maybe 1000 multiplied by 2, and still it will manage to identify the hidden details, and it may expose some of the different categories that may exist in the data set. So that's the whole idea of the principal component analysis. So how this principal component analysis works, this is something you should have studied in the lectures, but I will quickly show how to obtain the principal components. So principal components is same. So this, you know how to draw x and y. So principal components are again something similar, but you have some axes, we call them components in the PCA space. And the rule is, if you have row multiplied by column, you will get exactly row multiplied by column, that many number of principal components or PCs. So if you have 1000 rows and say 100 columns, if you apply PCA algorithm, you will get exactly 1000 multiplied by 100. So which means you will get 100 principal components. But since we are transforming the data into PCA space, so all this data 100 multiplied by 100, this will be in PCA space. So in PCA space, maybe only 2 dimensions, maybe component 1 and principal component 2. That may be enough to represent all the data in just 2 dimensions, and still we can represent all the data within this 2 dimension, within PC1 and PC2. So that's the beauty of the principal component analysis. And then how to get the principal components? So we have to follow some rule. So the rule is, you take the actual database, row into column, that's your original data, or you can call actual data, and then obtain the covariance matrix. Obtain the covariance matrix of the actual data set, which is row into columns. Yeah, so covariance matrix is always a square matrix, and the dimensions will be, so if you have a row multiplied by column, say 10 rows multiplied by 4 columns, your covariance matrix will be 4 multiplied by 4. So something like a column multiplied by column of the actual data set. So that will be the size of your covariance matrix. So in this case, you have if you go to our example back here, so you have 6 samples, so that makes 6 multiplied by 2, because you have only 2 columns. So that's the dimension of our data set. So our actual dimension of our data set is 6 multiplied by 2. If you take a covariance matrix, the size of that covariance matrix will be 2 multiplied by 2. So that will be the size of your covariance matrix. So let's call the actual database as maybe, how do we call it? Let's call data. Data is equal to our actual database, which is 6 multiplied by 2. We take the covariance matrix, covariance of data, so you will get 2 by 2 matrix. So 2 by 2 matrix. Once you took the covariance of your actual data set, get the eigenvalues. Once you calculate the eigenvalues, calculate the corresponding eigenvectors. So corresponding eigenvectors. So your so this, if you have 2 by 2 matrix, which is your covariance matrix, your eigenvectors will be 2 by 2. This is something that we will check now. And then you take that eigenvector, so you will get, since you have, where is that? You take that eigenvector, and then you take your actual database, which we named it as data, you multiply it by eigenvector, so that should give your principal components. So since we have 2 columns in the data, so we will get 2 eigenvectors, sorry, two principal components. So data multiplied by your eigenvector, so that should transform your data into PCA space, and in PCA space you will get 2 eigenvectors. So that's principal components, sorry, let's call it as PC1 and PC2. So that's the algorithm to get or to transform your data into principal components. And we also need to check, so based on your eigenvalues here that you get from covariance of from your covariance matrix, we can also rank the principal components. So say if you have, since you have 2 by 2 since our covariance matrix is 2 by 2, let's go to the next page. So if your covariance matrix is 2 by 2, you will get 2 eigenvalues, say lambda 1, lambda 2, and we have to check which one has the highest value. So if lambda 1 is greater than lambda 2, so you get the eigenvector of lambda 1, so which will be 2 multiplied by 1, that's the size of the eigenvector, and then lambda 2, that will be 2 multiplied by 1. So that's the size of the eigenvector that correspond to eigenvalue lambda 2, 2 multiplied by 1, this one. So that will be the size of the eigenvector that corresponds to eigenvalue lambda 1. And then what we do is you take the data multiplied by your eigenvectors that corresponds to eigenvalue lambda 1. And since lambda 1 is greater than lambda 2, we can rank the eigenvector or we can rank the principal components. So we can take the data multiplied by eigenvector that corresponds to lambda 2. So we have data multiplied by eigenvector that corresponds to lambda 1, and then data multiplied by eigenvector that corresponds to eigenvalue 2. So since lambda 1 is greater than lambda 2, the principal component that we obtain from lambda 1, we call it as principal component 1, and then the principal component that we obtain by multiplying data multiplied by the eigenvector that corresponds to eigenvalue lambda 2, we will call them as PC2 or principal component 2. So that's the PCA algorithm. So using this algorithm we can solve the given problem. So to solve the problem, first get the details. So what we have here is if we go back to the question, you have 6 samples. So our capital N will be 6, and then you have two variables, length and width. So let's call number of sample n, capital N. Number of sample is 6, and then the small n, number of variables. That's 2. So why do we need this information? We need this information to get the variance in the data, and we need the variance in the data to calculate something called the covariance. Yep. So let's do that one by one. And then how to get the covariance matrix. So covariance of data, so that's something you have. So let's call length is equal to x and width is equal to y. So we have x comma y. So I said covariance matrix is a square matrix, and since we have only two variables, you will get 2 multiplied by 2. And then if we have two variables, this covariance matrix will contain ordered pairs. So how many number of ordered pairs? So that will be equal to n square. So if you have two variables, that's 2 raised to the power of 2. So you have 4 elements. You have 4 elements in the covariance matrix. So one element here, second, third, and fourth in the covariance matrix. So that makes your covariance matrix. So 4 elements. So these are nothing but some ordered pairs. What do you mean by ordered pairs? Since you have x comma y, you can get 4 ordered pairs, which are x comma x, x comma y comma x, comma y comma y. Yeah. So you take the covariance of each of these pairs. So covariance of x comma x, covariance of x comma y, covariance of y comma x, and covariance of y comma y. So these elements make the covariance of data. So this is nothing but your covariance matrix. So how to define covariance of an ordered pair? Yeah. So covariance of x comma x, this is easy to define. So to define that, you have to define first variance. What's variance? So variance is something defined by the formula 1 by n summation of x comma I minus x comma average of x comma I, where I range from 1 to n. So what do I mean by that? So if you have a sample, say x1, x2, x3, say x comma n, so you take the average of this value, so that should give xi to the, so that's the average of all the x, and then n is your number of samples, so n is equal to n, and then you already know what is xi. So these are the 1 2 3 4, where I range from 1 to n. So variance of x in this case will be just given by this formula. Yeah? So 1 by n minus 1, summation of I is equal to 1 to n xi minus average of xi. Yeah, so that's the rule. And if it's a covariance of x comma x, so that will be this whole term I equal to 1 to n xi minus xi average multiplied by all the same again. So 1 by n minus 1, summation of I is equal to 1 comma n xi minus xi. Okay. So this makes covariance of x comma x is equal to 1 by n minus 1 summation of xi minus average of xi whole square. Yeah. And similarly, you can write covariance of x comma y. So this is just variance of x multiplied by variance of y, that should be equal to 1 minus n summation of xi minus average of xi the whole square, sorry, not whole square, multiplied by yi minus yi average of all the y's. Yeah, that should give the, where I range from 1 to n. So this should give the covariance of x comma y, and this should be equal to covariance of y comma x. And so I can write covariance of y comma x, that should be same 1 minus n minus 1 I is equal to 1 to n yi minus average of all the y's xi minus average of all the x. So that gives the covariance of y comma x. And similarly you can write covariance of y comma y, that should be equal to 1 minus n minus 1 divided by n minus 1 I is equal to 1 comma 1 I is equal to 1 to n, and then yi minus average of all the y's raised to the power 2. So that should give the covariance of y comma y. So you know how to get covariance of y comma y, y comma x, x comma y, and covariance of x comma x. So now we can make the covariance matrix. So let's write the covariance matrix. So this should contains all the elements, all the ordered pairs. So if you have x comma y, this should contain all the ordered pairs. So the element of covariance of the matrix will be composed by the ordered pairs depending on the number of variables you have. So covariance matrix, let's say covariance of the data called data, that should be equal to covariance of x comma x, covariance of x comma y, covariance of y comma x, and covariance of y comma y. So we need to calculate in order to get the covariance matrix. So let's calculate covariance of x comma x. So let's calculate covariance of x comma x. So if we go back to the original data, so as I said, our length is x and our width is y. So follow the pen here. So length is x and width is y. So we're going to use this data and then we will get the covariance matrix. For convenience, I'm going to write here the, let's call x, that is nothing but your length, y nothing but your width. So let's write the data here: 294, 273, 78, 81, 87, 41, 42, 43, 74, 74, 80. So let's take the average of x. So that should be equal to, I already calculated the value, this should be equal to 183. On y average, this should be equal to 59. Yes, and we already have average of x, average of y, and now it's easy to calculate the covariance of x. So covariance of x, let's calculate here, covariance of x comma x, sorry. So this should be equal to 1 by n minus 1 summation of I is equal to 1 to 6 in this case, where n is equal to 6, xi minus xi, average of xi, the whole square. So that should be equal to 1 by 6 minus 1, and then we take the sum of all the x minus the average of x raised to the power 2. So that will be 287 minus 183 whole square plus 294 minus 183 whole square plus 273 minus 183 whole square plus 78 minus 183 whole square plus 81 minus 183 whole square plus 87 minus 183 whole square. You sum all of them, all of these values, and then you multiply it by 1 divided by 6 minus 1. So you should get an answer of 12383. So that should give the covariance of x comma x. Similarly, you can calculate covariance of x comma y. Covariance of x comma y, that's as I said again, as I said before, it's equal to 1 by n minus 1. I is equal to 1 to n xi minus average of all the x multiplied by y minus average of all the y. So this is easy to do, so just again 1 by 6 minus 1, and then you just take x value minus the average, which is 183, multiplied by, if you go back to the table here, you have x1 y1, so take 41, so that should be 41 minus average of all the y is 59, plus again you go to the table here, 294 subtracted from by the average of x, which is 183, multiplied by 42 minus 59, which is the average of all the y. So do that. So it will be 294 minus 183 multiplied by 42 minus 59 plus 273 minus 183 into 43 minus 59 plus 78 minus 183 into 74 minus 59 plus 81 minus 83 multiplied by 74 minus 59 plus the last value, which is here. You have 87 minus average of x, which is 183, multiplied by the y, last value in the y, 80, minus the average of all the y, which is 59 again. So you sum all these values and multiply it by 1 divided by 6 minus 1. So that should give covariance of x comma y, which is also equal to covariance of y comma x. So that should be equal to 352 approximately. Yeah, so check that value. I think so far good. Now you need to calculate covariance of y comma y. So calculate covariance of y comma y. This is same formula. I is equal to 1 to n, in this case 1 to n, where n is equal to 6, and then yi minus average of all the y raised to the power 2. So that should be equal to 1 divided by n minus 1, and then you take sum of all the y's. So what is that? So that is 41 minus 59 the whole square plus 42 minus 59 the whole square plus 43 minus 59 the whole square plus 74 minus 59 the whole square plus 74 again minus 59 the whole square plus 80 minus 59 the whole square. Yeah. And here 1 by n minus 1 is nothing but 1 by 6 minus 1. So that should give you a covariance of y comma y. This value should be equal to 352. I think I did a mistake before. Your covariance of x comma y, this value should be equal to minus 2067. I already calculated, so I'm just trying to record how it's done. So you have covariance y comma x. This is minus 2067. That's correct. Yeah. So you have covariance of x comma x. That's equal to what? What's the value for 12383? It's a big number. Covariance of x comma y equal to covariance of y comma x. It's a negative in a value, minus 2067. Covariance of y comma y, some small number in terms of magnitude, So now we can write the covariance matrix, covariance of data. So that's equal to 1, 2, 3, 8, 3, covariance of x comma y minus 2067, covariance of y comma x, that is minus 2067, covariance of y comma y, which is 352. So that makes the covariance matrix. So that's one of the main steps in obtaining the PCA. So let's put a box. So once you manage to calculate the covariance matrix, just to check the size of the covariance matrix. So it is 2 by 2. This is something that we can expect as our measurables, which is small n, that's equal to 2. If n is equal to 2, then the size will be 2 by 2. That's the size of the covariance matrix. If n is equal to 3, then size of the covariance matrix will be 3 by 3. Say for example you have length, width, and let's say equivalent circular diameter. It's called the CEQ. 3 variables. Then you will have x, y, z. So in that case your covariance matrix will be equal to 3 by 3. So covariance of x comma y, covariance of covariance of x comma x, x comma y, covariance of x comma z, covariance of y comma x, covariance of y comma y, and covariance of y comma z. Finally, third row will be covariance of z comma x, covariance of z comma y, and then covariance of z comma z. So you will get a 3 by 3. So that's how things work. So these are some mathematical rules. So that's the PCA algorithm. Whether we like it or not, we have to follow these procedures in order to get the principal components from the actual data set. So once we have the covariance matrix, the next step is to obtain the eigenvalues. So obtain the eigenvalue of the covariance matrix. It's a very long procedure, but that's the only thing that we have at the moment. And it's a very good algorithm to reduce dimensions. Here it's very simple. You have only 6 multiplied by 2, but this algorithm will become really useful when you really have a huge data with 100 columns, 200 columns, and so on. So to obtain the covariance matrix, you should know the formula. Determinant of S minus lambda I is equal to 0. So S is nothing but, I'm going to call S is the covariance of data, your covariance matrix. So let's call covariance matrix by the symbol S. This is only for my convenience. So S is the covariance matrix. Let's check how much battery I have. 6%. So covariance matrix, and then lambda is the eigenvalue, and I is the identity matrix. So I will stop recording. I have only 6% battery, so I will continue in the next video. So in the previous video, I was explaining the rules of PCA. PCA is principal component analysis, and then we are trying to use PCA to solve the problem, where the problem is you have a data set, you have a length, and then you have the width of the 6 different crystals, and you are trying to reduce the dimension of the data. So dimension is, at the moment we have 6 samples or 6 rows, that makes 6, and then you have 2 measurable quantities, that makes 6 multiplied by 2, that makes the current data set, and you need to reduce the dimension. So the least dimension that you can expect is 6 multiplied by 1, and to do that we are going to use the PCA. And in the previous video I showed or I explain the rules of PCA. So this and then I also explain how to get the covariance matrix, and then from the covariance matrix we have to get eigenvalues and the eigenvectors. So before trying to obtain the eigenvalues and eigenvectors, I will quickly revise the rules of PCA. The rules are extremely simple. All you need is to look at the data set and just count the number of samples. In this case it's 6, and then the number of measurable quantities. In this case it's 3. Sorry, in this case it's 2. It's length and then the width of the crystals. So you need the capital N, which is the number of samples, to calculate something called the variance in the data, and you need the variance in order to get the covariance. So covariance of what? Covariance of the ordered number of pairs. So that's the rule. So we need to obtain the covariance of ordered number of pairs. So how many number of pairs that we can get from this data? For that you need to know what's a small n, which is the number of measurable quantities 2. So the number of ordered pairs that you can make is n raised to the power of 2. So that makes 2 raised to the power of 2. That makes 4. So you need this information in order to get some idea about the number of elements that you can expect to see in the covariance matrix. So I already explained in the previous video, we have x comma y, which means you can get up to 4 pairs, x comma x, x comma y, y comma x, and y comma y. And then you have to calculate the covariance of these ordered pairs, which is covariance of x comma x, covariance of x comma y, covariance of y comma x, and then covariance of y comma y. So that makes something called the covariance matrix. So once you have the covariance matrix, you need to calculate the eigenvalue of the covariance matrix S. And then once you have the eigenvalue, you need to get the eigenvectors, the corresponding eigenvectors. These are the rules that we have to follow. So let's write. So we already calculated the covariance matrix, which is given by S is equal to, so covariance matrix 1 2 3 A3 minus 2 0 6 7 minus 2 0 6 7 352. So that's the covariance of x comma x. This element is the covariance of x comma y. Just follow the pen on the screen, and then this element is the covariance of y comma x, and the last element, fourth element, is the covariance of y comma y. So that makes our covariance matrix. To get the eigenvalue, we have to follow the simple rule that comes from the matrices. So the eigenvalues of covariance matrix, to get that, you have to solve this expression. Determinant of S minus lambda I, which is equal to 0. So we know S is the covariance matrix, lambda is eigenvalue, and I is just an identity matrix. So just to expand it, so lambda I is just an identity matrix. So write, and then lambda multiplied by I, that should be equal to, so we are dealing with 2 by 2 matrix. That's the size of the covariance matrix. So the size of the lambda matrix, that will be equal to 2 by 2, and the diagonal elements will contain the eigenvalues, which is lambda multiplied by 1 comma 1. So that's the identity matrix. So if you multiply, you get something lambda 0 0 lambda. So that's the lambda I value. So you have to subtract this value from the covariance matrix, and then you take set the determinant value equal to 0. So let's do that. Determinant of s minus lambda I, that's equal to 0. So that means s minus lambda I, this should be equal to 12383 minus 2067 minus 2067 352 minus lambda multiplied by I, so that's lambda 0 and then 0 lambda. So you subtract these values. So you need to apply the matrix rule when you subtract. So 12383 minus lambda minus 2067 minus 0 minus 2067 minus 0 and 352 minus lambda. So that's this rule comes from the matrices. So all you need is to subtract the first element with lambda, second element with 0, and then minus 207 minus 0, and then 352 minus lambda. So you have something here, and then you set this value equal to, so you have to calculate the determinant of this matrix and then set it to 0. So how do you do that? To get determinant, so you have to multiply, just follow the pen on the screen, 12383 minus lambda multiplied by 352 minus lambda minus this whole value minus 2067 multiplied by minus 2067. And whatever the value you get, that should be equal to 0. So 12383 minus lambda multiplied by 352 minus lambda minus 2067 multiplied by again minus of 2067, and this should be equal to 0. So if you expand this equation and if you do it correctly, you will get a polynomial expression that looks something like that. Lambda squared minus 12735 lambda plus 86327, that should be equal to 0. So this looks like a quadratic equation. Sorry, it's not a polynomial equation. So if you have a quadratic equation of this type, so how it looks like ax squared plus bx plus c, that's equal to 0, where a in this case is equal to 1, b is equal to minus 12735, and then c is equal to 86327. And we know that if you have a quadratic equation of this type, then we can obtain the roots or the solution of that equation using the formula minus b plus or minus square root of b squared minus 4ac multiplied by c divided by 2a. So you have all this constant. All you need is to plug in those constant in order to solve this expression. So we have minus, where b is minus 12735 plus or minus square root of b squared is minus 12735 raised to the power 2 minus 4 multiplied by a value is just 1 multiplied by c value is 86327. It's a positive quantity. So divided by 2, a is again 1, so 2 multiplied by 1. So if you expand, you will get something 12735 plus or minus the square root of a huge number 161834917. Yeah? So if you take the square root of this and then divided by 2, if you take the square root, it will be 12735 plus or minus 12721, so divided by 2. So this should be equal to, so the moment what we are trying to calculate is lambda. So this lambda will be equal to 12735 plus 12721. That's going to be a big number. Divide by 2, comma. And another lambda will be equal to 12735 minus 12721. This is going to be a small number in terms of magnitude, divided by 2. So that will be equal to lambda equal to 12728, and then lambda equal to 7. So for convenience, I'm going to give some number. So first one lambda 1, 1 to 78, that's first eigenvalue, and then lambda 2, which is equal to 7. So this is not surprising. So if you have a covariance matrix or a matrix of size 2 by 2, then you will get 2 eigenvalues. So that's what you get. So the magnitude of this eigenvalue already carries some information about your principal component. So what you can see from here, lambda 1 is definitely larger than lambda 2, so which means the corresponding eigenvector of lambda 1, that should give something related to your principal component. So we can call lambda 1 as a principal component, something related to principal component 1, and then lambda 2 is something related to principal component 2. And something that you should remember, so if you look at your actual data set, you have x comma y, that makes 2 of your measurable quantities. So which means out of 2 measurable quantities, you can get 2 principal components, 2 PCs. But the goal of, or the purpose of getting the principal component is to reduce the dimension. So in reality, probably you may need less than 2 principal components to represent almost more than 95% of the data. This is something that you will realize at the end of this problem. So you have 2 lambda 1, lambda 2, that will help you to calculate 2 principal components. And from the magnitude of this lambda, we can get some information. So based on the lambda value, we can even rank the principal component. So as I said, if you have if you have 2 measurable quantities, you will get the maximum of 2 principal components, but we can rank the principal component, which one is the first one, which one is the second one. So obviously, to do that, you have to check the magnitude. So lambda 1 is greater than lambda 2, so which means lambda 1 will give the first principal component. And then we can also even calculate the number of components required to represent 95% of the data, or to explain the maximum variance in the data. So roughly it should represent 95% of the variance in the data. So this is a must rule for principal component analysis. So if you decided to use principal component analysis, you should know how to or how many number of components that we need to represent the 95% of the variance in the data. So how to get this value? So if we have the eigenvalues, so in this case lambda 1 and lambda 2, so let's write the lambda 1. So let's create a table lambda. So the first lambda is 1 to 7 to 8, and then the second eigenvalue is 7. So you have to take the cumulative sum of the lambda values. So 1 to 7 to 8, and here is 1 to 7 to 8 plus 7. And then the next column should be cumulative sum of lambda value divided by sum of the lambda value. So sum will be here 1 to 7 to 8 plus 7. So this will be equal to 1 to 7 to 8 divided by 1 to 7 to 8 plus 7. And then here 1 to 7 to 8 plus 7 divided by again this sum, which is 1 to 7 to 8 plus 7. So if you calculate this value, this will be equal to 0.99, and the second one will be equal to 1. So what this number 0.99 means, so it means the first principal component that corresponds to the eigenvalue lambda 1, which is equal to 1 to 7 to 8, that should be enough to represent 99% of the variance in the data. So which means even if you have 2 components, only 1 component is enough to represent 99% of the data. To be specific, to represent the 99% of the variance in the data. So if you decided to plot, this is something you did during the computer lab. So you used a MATLAB to get the staircase plot. So let's plot 1, 2. So 1 is the principal component 1, and second is 2 is the principal component 2. And you plot it against the cumulative sum of lambda divided by sum of lambda. So you will get some point around here. So let's assume this is 1. So you'll get a point here that's equal to 0.99 percentage or 0.99. So just follow the dotted line on the screen. And then if you add the second component, then you will represent 100% of the data, which means when you add the second component, you represent the total variance in the data, total variance in the sense, total variance in the two components. So sorry, I mean like the two measurable quantities, which is x and y. Yeah. So the take home message is you need only one component, which is the first principal component, to represent the 99% of the data. So once if you manage to calculate the principal component, and if you decided to plot your transformed data, that's something we are going to do now on the first principal component, then you will see that one single component, that it should be enough to identify the hidden details. Probably you will realize that one component will expose the existence of two different categories in the given data set. So that's what we are going to do now. So let's go to the next step. So the next step is to get the eigenvectors. So we can get the eigenvectors of both the eigenvalues, which is lambda 1 and lambda 2. But since our plot of cumulative sum divided by sum versus principal component clearly show that only one component is enough to represent the 99% of the data, we will just calculate the eigenvector of the lambda 1. So that should be enough to get the first principal component, and first principal component should be enough to represent the 99% of the variance in the data, so which means you can ignore the second one. But if you decided to calculate, nobody can stop. You can calculate the eigenvector of the second eigenvalue, lambda 2 equal to 7. But in this tutorial, I will just show how to get the eigenvector for the first eigenvalue, which is 1 to 7 to 8. So to get the eigenvector, the rule is simple. Again, you have to check your first year engineering mathematics notes. So to get the eigenvector of eigenvalue lambda 1, let's say, you have to meet these conditions. So what's that? S is the covariance matrix minus lambda, that's the eigenvalue that we calculated right now. And then I is the identity matrix again. U is the eigenvector of the eigenvalue lambda 1, and that should be equal to 0. So let's expand this equation. You should know how, okay, this is just a formula, but you should know how to write this in a matrix format. So S is 1, 2, 3, 8, 3. So this is just a covariance matrix. Minus 2, 0, 6, 7, and then 352 minus. So this is your identity this is your lambda 1, 0, 0, lambda 1 multiplied by u1, comma u2. This is your eigenvector of lambda 1. So this matrix which you are seeing here, lambda 1, 0, 0, lambda 1. So this is nothing but lambda 1 multiplied by I. So you should know by this time how to get this value. So this is lambda 1, 0, lambda 1, 0, 0, lambda 1 multiplied by 1, comma 1. That should give again lambda 1, 0, 0, lambda 1. It's a diagonal matrix, and the diagonal elements will contain your eigenvalues. Okay, so let's expand this equation. So to expand this equation, you should know the rules of how to subtract. Forgot to add something here. This should be equal to 0, comma 0. So this is a vector. So you will get two equations. So let's do that. 1, 2, 3, 8, 3 minus lambda 1 multiplied by u1 minus 2067 multiplied by u2, that should be equal to 0. And then the next one is minus 2067 multiplied by u1 plus 352 minus lambda 1 multiplied by u2 is equal to 0. How this comes from? So this comes from, so if you expand the, so you can expand this expression in the form of 12383 minus lambda minus 2067, so minus lambda 1, sorry, minus 2067 352 minus lambda 1. So, and then we are multiplying this with no, sorry, this is not correct. Yeah, you multiply with your eigenvector u1 minus 2067 multiplied by your eigenvector 2, which is u2, and then minus the second expression will be minus 2067 multiplied by the eigenvector, that's correct, eigenvector 1 plus 352 minus eigenvalue lambda 1 multiplied by u2, that's equal to 0, that's correct. So expand this equation. So I'm going to take only one expression. That should be enough to get the eigenvectors. So this is a very tricky expression. Since you don't have a computer, we can set some rules to solve this equation. So let's rewrite this equation. 12383 minus lambda 1 multiplied by u1 minus 2067 multiplied by u2, that's equal to 0. So take this minus 2067 to the right hand side. So 12383 minus lambda 1 into u1, that should be equal to 2067 into u2. And then 12383 minus lambda 1 u1. So take this 2061 to the left hand side of the expression, so divided by 2067, that should be equal to u2. Or, and then you take the other, this whole term in the left hand side to the right hand side, so it goes to the denominator. So u1 by 2067, that should be equal to u2 by 12383 minus lambda 1. So I'm going to call the whole term on the right hand side is equal to t. So which means u1 by 2067, that becomes just t. And if I'm going to assume if t is equal to 1, then u1 by 2067, that will be equal to 1, or u1 will become, u1 is equal to 2067. So you already calculated u1 for the condition t is equal to, condition t is equal to 1. So now you need to calculate u2. So we know u1 by 2067, that's equal to t, which is equal to u2 by 12383 minus lambda 1. So if t is equal to 1, then u2 will be equal to 12383 minus lambda 1. So we already know what's lambda 1. So lambda 1 is something around what's the value of lambda 1? 1 2. So this is 12383, 12383. So lambda 1 will be equal to 12728 minus u2 will be equal to 12383 minus lambda 1, that's equal to 12728. So that should give u2 value that should be equal to minus 345. So you already got the eigenvector u1 and u2, so that should be equal to, so u1 is 2067 and then u2 is equal to minus 345. This is something that you calculated by setting something is equal to t and you assume t is equal to 1. Yeah, so you got some eigenvector that corresponds to the eigenvalue lambda equal to 12728. So this is the eigenvalue of the principal component and this is the corresponding eigenvector, something that we calculated now. So you have to normalize this eigenvector. So if you assume t is equal to 2, then you will get a completely different answer. But if you normalize the data, you should get the same value. So how to normalize this? You have to take u1 divided by square root of u1 square plus u2 square, u2 divided by u1 square plus u2 square. If you try to solve the problem using MATLAB, normally your MATLAB will report the normalized eigenvectors. So this should be equal to 2067 divided by 2067 whole square plus minus 345 the whole square, and then again for u2 it's minus 345 divided by square root of 2067 the whole square plus minus 345 the whole square. So you should get a value. I'm going to call the first eigenvector by the symbol epsilon suffix 1. You should get a value of 0.986. You may get something similar in MATLAB. Maybe the sign may be different, but you should get a similar value if you decided to use a computer and if you're going to solve this problem using MATLAB. So what's this? This is the eigenvector of the eigenvalue lambda 1, which is it. So once you have the eigenvector, it's time to calculate the principal component. To get the principal component, it's very easy. You have to take the actual data set and then you multiply the actual data set with your corresponding eigenvectors. So your actual data set is a 6 by 2 matrix, 287, 41, 294, 42. So that's one is length and the other one is width. 273, 43, 78, 74, 81, 74, 87, 80. So that's your actual data set. You multiply by your eigenvector. So your eigenvector is 0.986 minus 0.164. So you have to multiply them. So I'm going to do it now. 287 multiplied by 0.986 plus 41 multiplied by minus 0.164. Take the second row, 294 multiplied by 0.986 plus 42 multiplied by minus 0.164. Go to the third row. In the actual database, 273 multiplied by 0.986 plus 43 multiplied by minus 0.164. Go to the fourth row, 78 multiplied by 0.986 plus 74 multiplied by minus 0.164. And then go to the 1, 2, 3, again 81 multiplied by 0.986 is the fifth row in the actual data set, plus 80 multiplied by minus 0.164, and finally you can get 87 multiplied by 0.986 plus 80 multiplied by minus 0.164. So that should give something called the principal component. So if you do it correctly, you'll get something like this, 277. I already calculated this value, so I'm just going to list it here. 65, 68, 67. So if you check the dimension of this data, this is 6 multiplied by 1, and we already know that this should be enough to represent the 99% of the variance in the data. So if you manage to calculate the remaining eigenvector of the second eigenvalue, which is lambda 2 is equal to 7, then probably if you add that second principal component, you will represent the 100% of the variance in the data, which is, but this is not necessary. Typically, if your principal component can represent more than 95% of the data, that itself is a good result. And so let's try to plot this value. So before plotting this value, it's something that you should know. So what we did is you took the actual data set, which is here. So this is typically in an XY plane, and then we calculated the covariance matrix, and then from the covariance matrix we got the eigenvalues. From the eigenvalues we rank the principal components. Once we managed to rank the principal component, you took the eigenvalue that corresponds to the first principal component, which is enough to represent the 99% of the data, and then we took that first principal component, we took that first eigenvalue to get the corresponding eigenvector, and then we are going to multiply that eigenvector with the actual data set in order to do something which is called transform the actual data set into space, which is called PCA space. So this number which you are seeing here, just to follow the blue or the blue line in the screen. So the numbers which you are seeing here, so these are some data. These are transposed data, and this data is considered to be now in the PCA space, so-called PCA space. So I'm going to plot this one. So I'm going to, since I said only one component is enough to represent the data, so I'm going to assume everything is on the first component, and that first component is something on the x-axis. So I'm going to put all y value is equal to 0, 0, 0, and I'm going to plot it. So if you actually plot this value, so let's say 0 is in the middle, somewhere you have 60, 120, let's say somewhere here you have 200, maybe 250. Don't scale because I just want to show how the data will look like if you manage to plot it on a graph paper. So if you plot 65, 68, 67, it will look something around here. If you plot 262, 283, 277, it will be somewhere around here after 250. So actually, if you look at this graph, what you can see here, you see two categories, which means with just one component, you manage to show that there exist two categories in the given data set. And this one component, this is the first principal component. Normally we use the symbol PC1. PC1 means principal component 1. So this problem is extremely simple, so that's why you can represent 99% of the variance in the data. But if you get more dimension, more measurable quantities, more number of samples, things may get complex, and sometimes you may need more than one. You may need at least two principal components to represent the 95% of the variance in the data, or sometimes you may need even three principal components to represent the 95% of the variance in the data. But this is something that you have to calculate based on your eigenvalues. So if you think, say like lambda 1, lambda 2, that represents 95% of the variance in the data, then you have to get the eigenvector of lambda 2 as well, and in that case you have to plot one component here, which is PC1, another component PC2. So PC2 will comes from the actual data set multiplied by the eigenvector that corresponds to second eigenvalue, which is the lambda 2. Sometimes you may need 3 principal components, so in this case you have to plot the third principal component, which is PC3. So this is something you have to calculate based on this value, cumulative sum of your lambda divided by sum of the lambda values. So this number will give some idea about how many number of principal component you need to represent the 95% of the variance in the data, and the lambda itself will give some idea about how to rank the principal components, like which one should be principal component 1, which should be principal component 2, and which should be principal component 3, and so on. So this is one way to get a principal component. Most of the software like MATLAB and some other software in the market, for example Crystallisation, so they use something happening here. So some softwares in the market, they use like Crystallisation. This is one software which is available in market. So they calculate the actual mean values, and then they subtract all the elements in the data set by the corresponding mean values. So what do I mean by that? I will show you now how to do that. So let's take the actual data set. You have 287, you have 287, 294, 273, 78, 81, 87, 41, 42, 43, 74, 74, and 80. So most of the software, they take the mean value of all the x and all the y, and if you have z, they take the mean value of z, and then they get a different matrix, which is 287 minus the mean value. So the mean of this value is 183, and the mean value of the y is equal to 59. So and you have to subtract all the elements in the actual data set in each of the column with the mean of each of the column. Yeah? So the mean value of each of the column. So 287 minus 183, 294 minus 183, 273 minus 183, 78, minus 183, 81, minus 183, 87, minus 183. And then you do the same for the y-axis, or the y column y, or the second column, or the second measurable quantity, 41 minus 59, 42 minus 59, 43 minus 59, 74 minus 59, 74 minus 59, 80 minus 59. And then you multiply it with the corresponding eigenvector. So if you do it correctly, you will get PC1 in the form 105, 112, 91, minus 106, minus 103, minus 98. I think the mean value will be centered around the 0, I think, for this type of data. So if you manage to plot it, so as we know that only one component is enough to represent 99% of the variance in the data, I'm going to assume that first component lie on the x-axis, so which means your y is equal to 0. Many software make the similar assumption. So they put the first PC1 on the x-axis, and second PC2 on the y-axis, and the PC3 on the z-axis. So we will follow that same rule. So if you plot these values, so you have 0 somewhere here and then 100 somewhere on the right hand side, minus 100 on the left hand side. So you can plot, just follow the red color ink on the screen. I'm going to plot the first 3. So you get 95 here, 105 here, 112 somewhere around here. So that makes one category. And then you plot the other one. So minus 106 somewhere here, minus 103 here, minus 98 somewhere around here. So that makes category 2. So again, obviously, you have 2 categories. First one may be category 1, second one may be category 2. So this one typically corresponds to your needle-shaped crystals. First, this one corresponds to your spherical particles. So that completes our exercise. So just remember the rules of PCA. PCA is a technique just to reduce the dimension. It becomes very handy and really useful when your dimension gets bigger and bigger. Imagine you have like 1500 rows, something similar to your coursework data, multiplied by 7 variable, again something similar to your coursework data. You can transpose all those data into PCA space. Probably you can represent almost 95% of the variance in all the data, which is 1500 multiplied by those 7 columns in just 3 dimension and sometimes even in 2 dimension. So it completes this exercise. Thanks for listening.